Hey, yes, yes. Uh, yes. Hello, everyone. My name is Lingzhen, a former member of the group. Previously, during my PhD, I worked on shape memory alloy strengthening, and basically similar topic as Ali is doing. And after my PhD, I moved to Hong Kong doing my postdoctoral research there. The topic is floating structures. And after a while, we refined the topic to modular floating structures. The engineering application could be floating cities, floating bridges, etc. At the end, I want to show you something really practical already in application in Helsinki, Finland. These are my collaborators, Associate Professor Tan Bi and Professor Xiaoyin Zhao. They are all professors at Hong Kong Polytechnic. Yes. This topic hears fancy at the beginning, but in Hong Kong, there is really a engineering application demand. For example, in this figure, the green parts are existing land or islands in Hong Kong, and these pink parts are the planned artificial island called Gaoyizhou Artificial Island. Most of the region will be land reclaimed, and the small part will be floating. So our work may promote the application of this Gaoyizhou Artificial Island. And existing floating structures are generally two types. The first type is a giant single floating structure. For example, a floating wind turbine and floating oil gas platform. The other type is made of modular floating bodies to form floating bridges, already applications in Seattle, the USA. And here is a very famous application example in Singapore. A floating initially it was designed for a national parade, but later on it turned to be entertainment platform, etc. Here is a vision from our colleague from Blue 21, a Dutch company. They are pioneers at floating solutions. The above part is the extension of continent or island or large island, and the lower part is a floating city or we say floating island. And as engineer, also scientist, we wish to capture the essence of floating structures. So we abstracted such a form. Each block is a floating is a floater. They are interconnected. On above, there could be a wind turbine, multi-floor buildings, etc. Already, there are a lot of water tank tests and numerical simulations on multi-modular floating structures. For example, 2 floaters, maximum 8 floaters, as far as I know. And a analytical design method is missing at the current stage. So we initiated this study, analytical design of modular floating structures. We focus on the mathematics of the structure. We summarized 3 types of modular floating structures: infinite, semi-infinite, and finite. These are very similar to the beam theory indeed. In infinite modular floating structures, the load is applied at the middle, and the length is, the edge to this concentrated load is longer than a characteristic length, lambda c. I will introduce it later. This property, lambda c, characteristic length, basically describes the region influenced by a concentrated load. And beyond this region, the influence, for example, inclination, etc., can be ignored. The second type is a semi-infinite modular floating structure. The concentrated load applied at one end of the structure, the other end is further away than a characteristic length. The third type is a finite modular floating structure. the total structure length is smaller than a characteristic length, or it could be of any length. And the load could be applied at any location. So the everywhere of the structure is influenced by any load applied. We will dive into these three types of structures. Here is the abstracted mechanical model of modular floating structures. Each floater is supported by a vertical water spring Kf and a rotational water spring Kr. Here I may introduce a bit more. Imagine if we have a floater or just a empty box. It is floating in the water. If we push it down, it tends to bounce back. If we lift it up, the gravity would drop it down. This behavior resembles a water spring. So in the inclination direction is the same. So we can use this vertical spring and the rotational spring to represent the water resistance behavior. And in between of two floaters, there is a connector with a bending stiffness Km and a shear stiffness Kq. So the equilibrium of a single floater is expressed this way. This system is essentially a discrete problem. So we need difference to describe its behavior. But the difference can be expressed as differentiation plus a residual term. And when we ignore this residual term, we could use differentiation to approximate the difference. Then after some derivations, derivation details are available in this paper, we could have this very nice fourth order differential equation. Z means the vertical displacement, or say deflection. So fourth order differentiation, second order, and zeroth order. In the auxiliary terms, mu and omega, they contain the influence of water spring stiffness, connector shear stiffness, connector bending stiffness, and the floater size. So from here to here is 1L. Then incorporating four boundary conditions, we can solve the problem. Here is the first type of the modular floating structure, infinite type. Due to symmetry, we only show half of the structure here and half of the concentrated load. The first boundary condition is very clear. Here at the close end, x equals 0. We only have half of the concentrated load. So this condition is obtained. At the far end, since the half of the structure is greater than a characteristic length, so the influence there is 0. For example, inclination, deflection, connector force, etc. They are all 0, but only 2 are independent. Therefore, we have boundary conditions 3 and 4. As for the second boundary condition here, M0, it requires some mathematical tricks. What I did is I analyzed the bending equilibrium of half of the structure. Then M0 here can be expressed as such a form. Each term is a function of concentrated force F and the geometry, etc. The reason I regard this important is sometimes, just a second, let me do it this way. Yes, here is the original fourth order differential equation. At some specific cases, for example, when the connector bending stiffness is sufficiently large, then we ignore the connector bending deformation. Then the problem reduces to a second order differential equation. So we can only satisfy 2 boundary conditions. But this one is automatically satisfied because it is derived based on a general equilibrium rule. So when we need 4 boundary conditions, like here, we take it as boundary condition. When not required, it is automatically satisfied. So 4 boundary conditions obtained, substitute in the fourth order differential equation, we have the final solution. Here shows one example. The dots are the numerical simulation results, and the curves are the analytical results. We notice here deflection, inclination, connector bending moment, also connector shear forces can be closely approximated. There are some noticeable error, but for example here, the inclination, the error is less than 0.01 degree. It's negligible error. Then we come to the semi-infinite modular floating structure. This time, still a fourth order differential equation, for boundary conditions, but much more straightforward. At the close end, the concentrated force and the bending moment, they are known. At the far end, things are zero. So with these four boundary conditions, we can solve the problem. And this time, the validation is nearly perfect because we do not have some special treatment, just very straightforward for boundary conditions. Then, what is the characteristic length in the system? As I mentioned at the very beginning, characteristic length characterizes the the length of the region influenced by this concentrated load. Since during the derivation, I noticed that if we consider simultaneously connector bending and bending stiffness and the connector shear stiffnesses, the expression is very complex, and at some point, non-solvable analytically. We only rely on numerical simulations. Therefore, I tried to analyze connector bending stiffness or connector shear stiffness, one at each time. So this figure shows the normalized characteristic length versus connector bending stiffness and connector shear stiffness. The dots are the numerical results, and curves, the blue curve represent this equation, analysis only considering connector bending stiffness. And this figure, red figure, represents this equation, the model considering only connector shear stiffness. I noticed that the lower value from these two analytical models are close to the numerical results. Therefore, I tried to have such an algorithm taking the lower value from both the bending model and the shear model. The updated results is represented by this mesh, and the dots are again numerical results. Despite some error here, it generally captures the characteristic length. Then the potential applications we have in mind. For example, the first one is once we build a floating platform based on modular floating structures, we have to apply superstructures. So we place everything on a single floater, or we distribute them on different modulus. The resulting deflection, etc., will be totally different, and our model can very well analyze the influence based on the rule of superposition. The second application is that after some years of use, we may change the functionality of certain floaters. For example, increase the floors of some buildings. The resulting deflection connect forces has to be analyzed. And just a few days ago, I realized even we move a new furniture into the system, the code is changed. So on the ground, we add something, there's not much difference, but adding anything on a floating system, water resistance may change. So it has to be balanced. So this is a further application scenario. This one shows the design of traffic layers. For example, we have a BOF view from a floating city. Some of the functionality, for example, laboratory is sensitive to inclination, etc. So we have to move the traffic lane away from such a structure. So the model can be used to design traffic layers. Yeah, the last one is I will show more details in the second part of my presentation with animation. So here comes the second part, finite floaters. Again, with the same topic. Once again, I use this figure to demonstrate in the previous 10 minutes, I talked about infinite modular floating structures and semi-infinite. But in reality, floaters would have would have finite size, and we would only use finite floaters to build a structure. And here shows an example. Also, load could be applied at everywhere. Therefore, the previous two models, they couldn't always work. Therefore, we need a finite modular floating structure analysis model. And very much inspired by this book written by Anthony, Beams on Elastic Foundation. He was a professor in the US, and he was the student of Professor Timoshenko. That's Timoshenko. Based on, inspired by his book, I noticed that we could use a superposition technique to analyze finite modular floating structures. Here we could place a infinite modular floating structure and the two semi-infinite modular floating structure to form to represent a finite modular floating structure. Here in the system, the concentrated force F is known, and we have four auxiliary terms, QR, MR, applied at one semi-infinite modular floating structure, QL, ML on another structure. Two potential applications are floating cities and floating bridges. I show you more a bit later. Yeah, first we look at the floating city case. Here, in my imagination, the floating city should be float, example, in the ocean, and the edges are free from restriction. This means they are free to deform, and the reaction force should be zero. Therefore, based on the rule of superposition, the load at this line, external load and internal load should be summing up, they should be zero. Therefore, we have this summation of Q zero and summation of M zero. Likewise, at the right edge, the summation of internal and external forces and moments should be zero as well. Therefore, we have these two equations. Four equations solving for auxiliary unknowns. This is mathematically reasonable. So solving these four terms and superimpose the behavior of these three auxiliary systems, we have the behavior of a finite modular floating structure. Here shows one example. Once again, the numerical results are shown as dots, and the analytical results are curves. We notice that when the total structure length is greater than half of the characteristic length, this flexible finite modular floating structure analysis model can very well capture the system behavior, including inclination, deflection, connector bending moment, and connector shear force. On the other hand, if the total structure length is smaller than a quarter of the characteristic length, then that model has some clear error. But a rigid modular floating structure can very well capture its behavior. A rigid modular floating structure means the connector is stiff enough so that we can ignore the relative displacement. Then the entire system is regarded as a rigid body. It is mathematically represented by a constant inclination and a straight line deflection, a straight line deflection. As for the situation in between, there are some discussions, but I skip from during this presentation. So we could summarize such a table, talking about different types of modular floating structures: infinite, semi-infinite, finite but flexible, finite but rigid. If you are familiar with foundation engineering, you should have read such a table somewhere, because I noticed foundation and the floating platform, their philosophies are quite similar. In foundation engineering, they have beams or plates. Here we have modular floating structure. In foundation engineering, things are supported by soil. In our case, supported by water. And the superstructures are superstructure. They are replaceable. So this is something, yes. And the last example is a floating bridge, analyzed based on the rule of superposition again. But this time, the floating bridges, the two ends should be connected to land, to shore. Therefore, the deflection should be zero at the two edges. And I consider that the two ends are firmly connected to the land, therefore inclination are zero as well. So we have these four resultant displacements. Once again, for equations, solving for unknowns, they are reasonable. And here I give an example of a quasi-static traffic load passing through a floating bridge from one shore to another shore. Here is an animation of showing how nice the analytical solution is. I show you once again. Traffic is from here all the way to the other shore. Then I want to show you some potential application in real world. So what I have been introducing are not really applied in real world. They exist in my computer, so should be generally correct. But during the conference in Helsinki early this week, we attended a technical tour. Here is a floating harbor in a city called Espoo, just next to Helsinki. Here, every block is a concrete floater. They are linked by something here. I'm not sure if how rigid they are. Is a hinge joint or a connected with certain stiffnesses? But we can basically use the modular floating structure model to analyze. So here is one floater, and here is another floater, likewise extended. The other application is in the finite modular floating structure model. I found such an application case. Here is one floater, here is another floater. Its one edge is linked to a much stiffer floater. Therefore, we can ignore its displacement. So both inclination and deflection should be more or less zero. And at the other edge, since there is no external force, so we take M0 and Q0. So the previous model didn't include such a specific boundary conditions, but by simple derivation, we can also solve such a situation as well. This is, I found, the closest case to my model. At the very end, since the group is very good at structure dynamics, I may introduce a bit about hydrodynamic behavior of modular floating structures. Still, I characterize the system as a rigid modular floating structure or flexible modular floating structure. I noticed that once the total structure length exceeds some length related to the characteristic length, the system can be again characterized as a rigid system. So its dynamic behavior is looking like what is shown in the animation. Here we consider the mass of the structure, added mass due to motion of water, damping from the water, etc. Basically, the story of structure dynamics. Just considering the wave loads, the wave pressure, etc., play an very important role in the system. The second case is a flexible modular floating structure. The requirement, the characterization requires a relatively flexible connector so that we allow relative displacement among different floaters. Basically, the motion profile of the floating structure follows the profile of the wave. I will show you one second. This is the real world application. A floating entertainment platform near Hong Kong. I took this video myself. Once again, the profile of the floating platform aligns with the profile of the wave surface. So thank you very much.
Thank you, Lingzhen, for this very nice presentation. Do we have questions here or online?
Yeah, and also, thank you, Eleni, for the invitation. I'm not sure if she's from Apple.
Actually, I have a couple of questions.
Yes, please.
Nice, interesting presentation, but the dynamics are, I think, that are a little bit more complicated with respect to the aim that you have and what I'm talking about. So let's say starting from the last video, where you have the floating structure that moves along with a wave, let's say, excitation, it's reasonable.
But when you mean this one?
No, the very last slide that you shoot, no, this one.
Okay.
But when you want to build, let's say, a floating city,
yes,
you cannot allow for this.
True.
I cannot sit on my kitchen and go like this, right?
True.
So this implies if you go to kind of an engineering perspective of what you have described, I think that first of all, you have more boundary conditions. And what I'm talking about is that the fact that your floating structure should be constrained to the ground anyway, right? Either close, let's say, to a harbor, or to the
seabed.
Yes.
So with some chains.
Yes. And this by default, chains or blocks or whatever. So I mean, this reminds me, how do we call media?
Muscles.
Muscles. I have a friend that grows mussels, right? And he has a floating structure with ropes, barrels, right? And the mussels have been hunting and grown. In order to have this fixed, in the sense that he need to go the other day, and this will be, I don't know, 100 miles away, he will constrain them with ropes and blocks up to the
yes, we come more in line.
Exactly. So this, by default, let's say, changes completely the boundary conditions, right? Isn't this something that you should take into account in your analysis?
Something I didn't introduce is it is true that for floating bridges and floating cities, such a large motion is not allowed. Here, I just give you an example about what we have already seen in the real world, because these floaters are very lightweight. We can basically lift them by single hands. But in reality, the floaters could be concrete boxes, which are few tons per floater. And there, things change a lot. And the one I shown at the very beginning, the free floating bridges in Seattle, they have a lot of mooring chains. So
to be constrained, let's say.
Yes, limit its dynamic motion. And what I have introduced until this page, things are dynamic. No, things are static. the reason I started from static are two. The first is that at the beginning I wasn't very good at dynamics, so I tried to do something that I am good at. The second reason is before dynamic, we should at least satisfy all the static requirement. For example, when you imagine if this is a ship or a floating something, we apply loads, it shouldn't sink. And shouldn't sink is the first thing, the connectors shouldn't fail. The better is that it doesn't even have plastic deformation, etc. And that's the capability of the models I introduced. And from this page on, it's hydrodynamic behavior. And I just started a few months ago. And I try to capture its sort of the basics. For example, the rigid one or the flexible one. And later, there should be more in line. I give you a quick drawing.
But including more lines, this is just a simple boundary condition in the end.
Yeah.
Yeah,
There is
my issue is that I guess that this is something I understand that it's something that you would like, let's say, to introduce. You would not be so much. I mean, it's a difficult problem because voltage to reduce vibration and wave dynamics and all this stuff. But wouldn't it make sense to start working on the scale you are imagining to work? You know what I mean? So it's different to have a barrel, let's say, that I can lift up with my hands, and different, let's say, to design a floating city. Wouldn't that make sense to work at that scale? That actually changes the whole dynamics. You know what I mean?
I guess I understand. Just at the laboratory level, we have difficulty to very soon jump to that scale. So at the moment, those experimental setup and let's say specimens measurement, all these things are very lightweight.
Yeah, that would be my second question. If you have some experimental results as well.
Not at the moment.
Okay.
I tried to use others experimental results to identify numerical model.
Okay, but because this would be also very nice to have an experimental.
I try to have it next year.
Yeah, that would be very interesting.
And then yes, this is like a dynamic problem, is what you were saying before, that you have noticed that you change the furniture and already like it changes your structure. So in reality, it is a dynamic problem. And actually, what it reminded me directly before you went like to the second part of your presentation is something that I was doing during my PhD. So I was working on vehicle bridge interaction, and sometimes we're taking into account the soil. And exactly this principle, like of the moving unit load on this kind of foundation, is what we were using to take into account the tracks on the ground. But we were using like the Winkler springs in order to consider that. And it was the same logic, like the central element that was like the finite, and left and right semi-finite elements. And like there is a book from Y.B. Young. He has worked a lot on this problem, but he's using exactly the same principle that you were using there. And he was using like this, I can share it with you if you want, like this unit load to derive also like analytical solutions. It reminds me the same problem. It's always dynamic. And I wanted to ask, like, how do you define the parameters like of the springs that you are using? Is it, I have no idea like about, how like water behaves and so on, like, or buoyance, like how do you define these parameters that you use in your model? Like in real structures, like is it always the same? How do you define these springs that you were using?
The springs, computational springs are quite simple. For example, this you call pontoon or box type, the water stiffness are just rho g multiplying the water plane area.
Okay, so it's like you can just you're pretty confident with what because it's the difference with foundation dynamics. There you don't know anything about the parameters, you assume.
Yeah, as far as I know, things related to soil you have to measure every time.
Exactly, you have to measure and
At different location, drag different cores and test.
So I guess it's more like it's always water. So I guess like how you estimate it, it's not.
You come the force.
Yeah, exactly. I mean, I didn't know, that's why I was asking.
But this is all considering conservation of potential.
Conservation for
potential theory in hydrodynamics. So everything is static, then you can use these
Yeah.
equations. But if
at,
not,
at the moment is yeah, most of things are steady.
Okay, yeah, I'm talking about
because once you move into the real wave loads, then you use the spectras for the wave spectrum and then also for the currents and these things, and then these things they make much bigger.
True.
Oh.
These things could be much more
Business
complex.
spectrum.
But basically, in real world, we have wind load and wave load.
Yeah.
In terms of wave, we have wave and current. Wave, so linear wave, higher volume.
Yeah, it's a function of the depth. It's a very complicated spectrum. The wave spectrum. I remember the name of the guy. It's a very
Swap spectrum.
Eh?
They use the one swap spectrum in offshore.
Yeah, one is this one. Yes.
From North Sea.
Yeah.
And also regular wave and stochastic waves. It's quite complex.
But if you also include mooring lines, then you also have another challenge, which is damping in the mooring line itself, because it's a flexible structure.
I'm not considering mooring.
But if you do it at some point, there's been work in Norway about this and the floating structures there.
A lot. NTUT, no, NTU,
Yeah.
they are quite good at this.
Yeah, and also Sinter. Also the companies in Norway, they're doing a lot of this on the scale that they're interested in for purchase.
Yes. And also for floating wind turbine. Scandinavian countries are quite good at it. There is a local requirement. Their seabed is not so flat like in China. The seabed is 2 meter, 4 meter, then gradually to 30 meters. But in Scandinavian countries, maybe 20 meters away from shore, the water is 40 meter deep. So they have to use floating, not anymore jacket type.
Yeah.
That's major reason how they're good at this field.
Nice. Start frequencies, spectrum analysis yet.
I tried something very simple. So ignoring some nonlinear terms and linearizing some nonlinear terms. I tried already a frequency analysis and plotted the structure motion versus wave frequencies.
And how does it look like for your flexible structures?
So for a rigid structure, there are two major frequencies, one rotational, so inclinational one, and one vertical one. There are some peaks in terms of like resonance, but not real resonance. And for flexible ones, the structure has several vibration frequencies, so we may see a few peaks in the let's say response spectrum.
Maybe you can borrow some techniques from wind engineering.
I'm trying to get something from bridge engineering because it's very similar thing, but
Yeah,
from wind, yes,
yeah.
from
Davenport. Yeah, he was the guy who invented the method that is used in Europe now for wind structures.
things. I'm trying to get reports.
Yeah.
I don't know if you have any more questions, maybe let's say.
I have maybe a short one. The examples that you showed in the beginning with wind turbine platforms and also the oil platforms, do you know how are they fixed to the sea ground somehow? Or are they?
Yeah, these are introductory things. It's as
Because they are also not really shaking a lot like the.
they shake.
They shake a lot.
They
So
shake.
they are not fixed at all.
And they are
Not linked to the ground. So for
another section.
wind turbines, there are let's say two types. One we call standing one or ground fixed. We have jacking platforms linking this place to the seabed. These are usually applicable to sea depth less than 40 meters. And over this boundary, the price is much higher for construction and design, etc. And for water depth larger, floating ones are more suitable. And the bottom of the floater is linked to the ground via mooring chains. So ropes usually metallic at the moment. And some researchers are considering composite ropes or composite mooring lines.
But yeah, as Vasily said, I think you need that also for your cities.
Yes, and mooring analysis for mooring line is quite complex. It's a quite nonlinear behavior.
Like the problem.
Very complex.
But without that, you start to have real issues also out of the plane that you investigated until now. Because the water moves.
Not yet announced.
I know, I'm aware, but without fixing your platforms horizontal.
It's the what? Accumulation of drift.
Yeah.
Floats everywhere.
No, even if it's linked to the land, it will still, you will have start having bending of the whole system
yes.
for out of plane.
Yes.
The same problem.
But it,
I know they also have some issue where they, instead of having more lines on every platform, they have between each, so a cluster of floating wind turbines that's maybe more similar to your problem with more between each platform.
Also, they connect, they have, let's say clusters
Yeah.
of floating.
Yeah.
Yeah.
That
And-
I read something from online. That one is mostly used for controlling system and transportation of electricity. It's less about structure itself, because for wind farms, then there's a term. Each wind turbine should be distant, how distant from each other, like 50 meters away or even 1 kilometer away. Otherwise, the energy absorbed by the first one cannot
have wake.
recover, the wake effect, basically. And in that regard, ropes linking or cables linking adjacent wind turbine are for controlling electrical devices, etc. It's less about modular. It can be both controlled. But yeah, also I'm thinking for the I may consider it later. Nice.
Good. Do you have any more questions or comments? If not, let's thank again Lingzhen.